Example one, let's do a homogeneous linear differential equation just to start off with a simple one. So go ahead and write this stuff down. So we want to solve dy dx minus 3y equals 0. You could, this is separable, so it's much easier to do than this, but it's kind of gets us to the right form and apply the technique and method, just kind of maybe see it a little easier at first off. This is already in standard form, right? So I wrote standard form down again. So you want to be able to recognize your p of x, q of x, and of course dy dx is on its own. So from that, we can see that what's p of x? That's just -3. So I'm just going to rewrite stuff over here. P of x, we can see, is just -3. It's homogeneous, so then q of x is 0. So mu of x is our next calculation. Remember, so you do standard form, figure out your p of x so that you can do your mu of x. So mu of x is e raised to the negative, no x there, -3dx. So that's just equal to e to the -3x. So that's our integrating factor. So then we're going to multiply by mu of x, which equals e to the -3x on both sides. So you get, and I suggest you show all these steps. You don't have to write everything out like I am, but you need to show these steps so you can start building the form in your mind. E to the -3x dy dx minus 3 e to the -3x y. Okay, so I'll highlight it in a second. Equal, and then you multiply it on the right-hand side, but it's just 0. So it's equal to 0. So this is the part you don't have to show. Like, this is the right form. So that is your e to the -3x dy, this whole thing here. So that's where the formatting comes in. I was going to highlight this. So you multiplied by mu on both sides. So you get, so here's your mu. So here's mu here, and then you did it over here, but it's 0 anyway. Okay, so that's what you multiplied by. Okay, so that is equivalent to the form, and this is the part you gotta kind of see, that is already that form of d dx times mu of x y. That's what you built by choosing your mu of x. So now you integrate both sides, and this time I'll show it. You don't have to always show all these little details. I'm going to show it because this is what you do. So d dx of e to the -3x y dx equal to, and you're integrating 0 dx, which is just a constant. So that is equivalent to e to the -3xy. And in case I didn't say it directly, explicitly, anytime you integrate the derivative, you get just what's inside. So that's the fundamental theorem concept. So you're undoing the antiderivative. So it's just itself. And the right-hand side, integral of 0 is a constant, because if you differentiate, you get 0, right? Okay, so then that's if and only if y is equal to c e. I'm just dividing by. So now I'm solving for y. I didn't say that stuff. So you divide by both sides, or this comes up in the numerator, so you get c e to the 3x. And that is true for all x in the reals. And also note that is the explicit form. This is an explicit form. Okay, let's do another example. So this one is going to be the same. I'm going to write the same one above, but I'm going to make it equal to a constant. I'm building in degree difficulty here. So let's do that. So next example, 2, solving a non-homogeneous linear differential equation. So let's solve this, but now we're going to set that equal to 6. So same method as above. So apply the same method in example 1. So your mu of x is equal to e to the integral negative 3x dx. So you evaluate that and you get the same thing. And then you multiply on both sides. Okay, so you multiply on both sides and you get e to negative 3x. Let's put this all the way to the left. E to the negative 3x dy dx minus e to negative 3x y equal to 6 e to negative 3x. So what's really different, right, is that this side in the above canceled out completely. It was just 0. This side's the same. All right, so that is equivalent to, or if and only if, you have dy dx. So remember, the left-hand side, you rewrite it in this form. So that's the mu y. So it's e to the negative 3x y. Right-hand side is now different. So it's 6 e to the negative 3x. So you integrate on both sides again. All right, so you have all of this. And I'm going to show it just so you see how you integrate on both sides. Like this. So this is dx. dx, okay. And left-hand side, of course, is just e to the negative 3xy, e to negative 3xy. Right-hand side, in this case, is pretty straightforward again, too, because it's just a constant there. So it's just negative 2e to the negative 3x plus c. So then you solve, and you get your explicit form as well again. So so y is equal to negative 2 because so when you divide, this guy's gone, but it ends up over here. So it's negative 2 plus c e to the 3x. And that's, again, true for all x in the reals. There's no restriction on that. Okay, so let's put it back up here. Look at both of those. You can pause it or whatever, or make sure everything's how you want it. And we'll go ahead and do one more. Okay, so this is example 3. Solve x dy dx minus 4y equal to x to the 6th e to the x. Okay, so the first thing you do is what? Okay, so first write in standard form. Okay, so go ahead and do that. So this is where I'd have you work ahead. Okay, so or on your own, maybe in class. So work on this on your own, and then I'll write it out. Okay, so to divide, to get standard form, divide both sides by x. And so we have dy dx minus 4y over x equal to x to the 5th e to the x. And I'll say this here, I wrote it later, but notice that this form here, there's really no restriction on x. X can be anything, but once you divide by x, then you have a restriction. So 0 is a problem. When you do that, you're introducing points that are undefined, and those points, or those values are called singularities. So singularity is when you introduce basically undefined values, and that's what happened right there. But it allows us to solve it, but initially there's no restriction. So you got to be really careful of that in differential equations. Okay, I'll write that up a little later. But anyway, so now you apply the process. Since this is in standard form, we have p of x, and you don't have to write all these out. Well, I don't know. I like to write these out. P of x is negative 4 over x. Q of x is x to the 5th e to the x. Okay, and then your singularity is 0. But you basically just introduced by doing this. So because it's non-zero and you basically don't want to skip around it, so either you want to take essentially the positive case. To make these simple, we are going to we will assume that x is positive, greater than 0. So non-zero, but we're just going to take the positive case. So you'll see the books just kind of throw that in there, and you're like, why do they do that? Well, it's because there's a singularity in there, and you have to make it well defined. So if you skip around it and go left, right, then it becomes a next level complicated. So let's just say it's positive, at least for this one. So anytime you see absolute values, you can drop them because of this. Okay, so let me put that in red or some pink. We may drop absolute values when you do your integral of 1 over x dx. Okay, so that's just kind of a forewarning. All right, so what is next? Calculating mu. Yeah, so mu of x is equal to e raised to the integral of negative 4 over x dx. So when you calculate that, that's just e to the ln x to the negative 4. And so you apply a property of exponents. So that's just x to the negative 4. So inverse property. So you got to picture basically this negative 4 here, just factor it out. And so integral of 1 over x is ln x. And so you end up with e x to the negative 4. Okay, we'll move on. All right, so then multiply on both sides. So multiply on both sides. by x to the negative 4. Okay, so then, oh, and I wrote this in just for so you see it. So we used the fact that e to the ln z is equal to z for z greater than 0. Just a little side note there. So let's show it. So x to the negative 4 dy dx minus 4x to the negative 5y equal to xe to the x, simplifying the right-hand side. So left-hand side is just your d dx of x to the negative 4y equal to xe to the x. Now you integrate both sides. You have d dx x to the negative 4y dx equal to the integral of x e to the x dx. So when you do that right-hand side integral, that's integration by parts. Hopefully you recognize that. So look that up if you don't remember straight up. Look up how to. That was an easy one, but look it up. So then you get left-hand side is just x to the negative 4y, and then you end up getting x e to the x minus e to the x plus c. And then you solve. So y is equal to x to the 5th, e to the x minus x to the 4th, e to the x plus c x to the 4th, and that's for x greater than 0. So you divide by the x to the negative 4, you're basically going to add 1 to this. Here comes up to the numerator, and then again numerator. Okay, and then I did say this earlier, I wanted to write it up. So note values for which, it's not Q, sorry, A sub 1 of x equals 0 are called singular points. Or values. Or a singularity. So in physics type stuff, that's where you get singularities, or where you get, you're dividing by 0. So you get an infinite mass or something like that. And those are black holes, essentially. So when you talk about a singularity in physics, that's essentially a black hole. So those of you who watch sci-fi stuff, you look at singularities, or when they say that, that's what's happening. And it's essentially dividing by 0. And not this class, but interesting stuff.